In this lecture, we will see one of the fundamental blocks that allows you to encrypt large messages, and in particular to design stream ciphers, and those blocks are block ciphers. So as their name indicates, they're only going to apply to small subsets of the message, but we'll see how their modes of operation allows us to encrypt large messages. So block ciphers, as I said, will be the building block of what we will use to encrypt large messages. From a very high level perspective, these are just functions that have a domain, and every evaluation requires a key in the key space, and it maps to a range. And we will require that those block ciphers be random looking among the space of functions. And we will see that there is something to be said about those functions that have the bias of being a permutation of the set X, because those block ciphers in fact are permutations because we require that they be invertible. And then we'll see how those block ciphers can be used for certain modes of operations once we've acknowledged the definition of what it means to look random as a function. So as a function operating on a small block, those block ciphers need to look random, as in could look like the evaluation of any function. And then how do we use a block cipher that operates on just a small block to encrypt a large message? So we to introduce the notion of a secure block cipher, we need to talk about pseudo-random functions, because that's what we want a block cipher to be. So we want a function that operates on a domain, maps elements of the domain to the range, and every evaluation requires a key in the key space. And we want to define what it means for a pseudo-random function to look random. Okay, and what it means essentially, informally, it means that given a computationally bounded adversary, that adversary must not be able to distinguish evaluations of that function for a random choice of the key from evaluations of random function taken in the space of functions from x to y. So to do this, to formalize what it means for an adversary to, or to compete in that security game, we'll define something very similar to the semantic security game. So there's going to be two experiments, and in experiment 0, the adversary stands in front of a box that returns evaluations of the pseudo-random function. So the behavior of the adversary is to choose elements in the domain, and the challenger chooses a key, very much like in the semantic security game, and the adversary requests the evaluation of that function at the key k on the elements x1 to xg, which of course the challenger sends back to the adversary, and the adversary returns 0, 1, which you can think of as, for example, 0, this is not randomness, 1, this is randomness, okay? But it doesn't really have to have a formal meaning. It's just a binary behavior. And of course, the binary behavior needs to be compared with the binary behavior in the experiment 1, where everything remains the same except that the challenger chooses a random function in the space of functions from x to y and returns evaluations of that function. So the game is between the adversary and challenger. The adversary chooses elements in the domain. The challenger this time chooses a function at random in the space of functions from x to y, and the adversary requests the evaluation of the xi, which they receive, and upon reception they decide 0, 1. Again, if it helps, you can think of 0 as saying it is not randomness, and 1 saying it is randomness. The edge of the adversary, of course, is the difference in terms of behavior between experiment of 0, 1, which is defined exactly the same as the semantic security game, which is we define the event W0 as the adversary returning 0 in the experiment number 0, and W1 as in the adversary returns 0 in experiment 1, and the adversary is the difference between those two values. So let's work out an example. So we consider the easiest case possible, which is the domain, the range, and the key space are all 0, 1. And the definition of the pseudo-random function is to XOR the input by the key. Okay. Now, do we have a pseudo-random function? Well, let's say our adversary. So first, we notice that the space of functions, so let's call it func from x, y, is made of the function that maps 0 to 0 and 1 to 1, the function that maps 0 to 1 and 1 to 0, and then the function that maps 0 to 0 and 1 to 0, or 1 to 1 and 0 to 1. So these two are permutations, and we know that our pseudo-random function is a permutation. So the way we can define our adversary is adversary decides to ask for the evaluation at 0 and 1, okay, and then when the adversary receives y1 and y2, and it doesn't know exactly if that is evaluation of our pseudo-random function or some random function, the adversary returns 0 if y1 is different than y2, and 1 if y1 equals y2. Okay, and in the case, the event W0, which corresponds to returning 0 in experiment 0, well, in experiment 0, y1 is always equal to y2, so the probability of W0 is going to be 1, while the probability of W1, which is that the adversary returns 0 in experiment 1 when only half the functions, so this is just the half of the functions that will satisfy that y1 is different than y2, otherwise in the other half y1 is equal to y2. Okay, so then in this case there's only a 50% chance to return 0, and therefore the advantage is equal to 1 minus 1/2, which is 1/2, which is non-negligible. So it is not a secure pseudo-random function, meaning that function is distinguishable compared to all the functions from x and y. Now let's look at a pseudo-random permutation. Okay, so we'll define everything the same, except that this time we're looking at a function that permutes elements of x, okay, instead of just mapping x to y, whatever is y. And when we want to formalize what it means to look random from the perspective of a computational bounded adversary among, this time not all the function, but just among permutations. And then everything works the same here. Experiment 0, you have the adversary that will receive an evaluation of the xi's that they request under the pseudo-random permutation. And in experiment 1, the adversary will receive the evaluations of a function chosen uniformly at random among all the permutations. Okay. Now the question is, what is the advantage? Well, first let's just see the definition is going to be the exact same definition. So the difference between probabilities of returning 0 in experiment 0 and experiment 1. So now, what is in our running example? Do we have a pseudo-random permutation that is secure, meaning like it's hard to distinguish, not this time from all other functions, but all of the permutations? Well, let's see. This time the permutations of x is exactly the set exactly made of two functions, the one that maps 1 to 1 and 0 to 0, and the one that maps 0 to 1 and 1 to 0. So there's only two permutations. Okay, and it turns out this one is exactly a choice. So a choice of k is exactly a choice of one of those two permutations, basically. So that corresponds essentially to k equals 0, and this is k equals 1. So it's gone. The previously defined adversary does not have any significant advantage. So the advantage of the previously defined adversary this time is going to be 0, meaning that they cannot distinguish just by testing whether or not the values they receive are different. They cannot test whether or not this is evaluations of f versus evaluations of the pseudo-random permutation. Now here's the thing. The block ciphers, their functions from x times k to x, such that there is a decryption function. So they're essentially pseudo-random permutations, but we want them to be secure as PRFs. So secure, indistinguishable, not just among the permutation, but also among all the functions. Now, it just so happens that the fact that those previous, the function f that we previously defined over x equals 0, 1, the fact that it was a permutation was exactly what gave it away as non-random. So one could argue that it probably is the same for all block ciphers, but in fact, this bias is no longer exploitable as the size of the space x increases. So there is what's called the switching lemma, which is we're not going to prove, that says that the difference between an adversary in the PRF game and an adversary in the pseudo-random permutation game is bounded by something that depends on the number of queries and most importantly the size of the space. So when the size of space is large, then that difference between those two advantages is small, meaning that getting a secure pseudo-random permutation for which this advantage is small means that we also know that this advantage will be small as well. Okay, so the moral of the story is that there is hope for block ciphers to be secure as pseudo-random functions, although, as we saw before, some pseudo-random permutations were not secure because of the fact that they were permutations, but there was in the case where the size x was small. So now let's see a historical example, which is the data encryption standard, which was a standard from the 70s to the early 2000s. This is the design. So this time we're talking about real life ciphers, so it automatically is a lot more complicated than the toy examples that I present in this class. So the input has 64 bits, and then it gets permuted from public permutation and then divided up between two halves, and one of the halves goes into what's called a Festel function, and the output of that gets XORed bit by the first half, and then things get swapped. So the left hand side goes to the right hand side, and so on and so forth, and you repeat 16 times until a final permutation, and that's the output. And here you have subkeys, so the master key has 54-bit and the subkeys have 48 bits. Okay, and so then what does the Festel function do? Well, if we zoom in, we have that each half block needs to be XORed by the subkey. So first it goes through an expansion function that packs the information into 48 bits, so it expands, adds some redundancy. And then everything is divided up into 8 blocks of 6 bits, and each go into what's called the S boxes, and these are essentially non-linear, so as far as possible as a XOR operation is the moral of the story. And then everything gets permuted one more time and gets out of the Festel function ready to be XORed with the other block. Okay, so that was a very famous standard. Now it's been superseded by what's called the AES, the Advanced Encryption Standard. Now let's move on to modes of operation. So the most straightforward mode of operation one can think of is what is called the ECB mode, which stands for Electronic Code Book. What it means is you just take your plain text, separate it, divide it out by many blocks that are a multiple of the length, the size of blocks that the block cipher works on. Each block gets independently encrypted with the same key. Okay, otherwise the key would have to be as large as the message, and you may as well use the one-time pad, so it's the same key here. and then you get blocks of the ciphertext. Okay, and decryption, of course, is also made blockwise. Okay, so each block gets decrypted in. Now, why is this insecure? Well, let's see. In our semantic security game, what would happen? Let's say an adversary chooses two blocks of the same length and build the following two messages. One is a repeat of the first block, and the other one is just a concatenation of the two messages. So the adversary sends those two messages. The challenger encrypts MI, where I, of course, that's in experiment I. Okay, so in experiment 0, they encrypt always M0, and experiment 1, they always encrypt M1. They send them back, and then the adversary decides. So basically, a repeat, if the ciphertext looks like C, let's say C0 concatenated with C0, then you know it came from the encryption of M0. But if the ciphertext looks more like C0 concatenated with C1, then it must be the encryption of M1. So the advantage will be won in that security game with an adversary deciding that way. So it's actually insecure. One way to visualize the semantic insecurity is to look at an image, the encryption of an image pixel by pixel. So this is the image. Each pixel can be encrypted independently, and because of this sort of deterministic map between, say white always goes to the same encryption, then this is pretty much what you would expect with the encryption of ECB. Which means you don't really know exactly which colors you had originally, but you certainly see the shape of the image that was encrypted. So it's very insecure. It definitely leaks information about the plain text, as opposed to with other modes where you see something that is more like random looking. Each block should look like it could have been anything. So here is one way to avoid that, and so this time you divide out the message according to blocks, and then the first block gets encrypted, gives you the first block ciphertext, but then that ciphertext is reused to be XORed with the second block of the message, and then that result gets encrypted and gives you the second block of ciphertext, which itself gets XORed with the third block of the plaintext, and so on and so forth. Okay, now two things. First of all, this cannot be done in parallel, so there is a cost to doing this, and also if you make a mistake, say one ciphertext has a mistake in it, then every subsequent blocks will have mistakes, so that can be annoying. Of course, the decryption works exactly the same way, meaning ciphertext 1 gets decrypted to get you the first block, but then of course that ciphertext needs to be XORed with the decryption of the second ciphertext, giving you the second block, and so on and so forth, with the same caveats, not doable in parallel, and subject to the consequence of decryption errors can be that the rest of the message is incorrect. Now, last block that I would like to mention, last mode of operation that I would like to mention, these are not the only ones, and I invite you to look at references, even like the Wikipedia page of modes of operation. So the last but really interesting mode of operation I would like to mention is the counter mode, because this time what we do is basically we turn our block cipher into a stream cipher. And the key stream is created by encrypting with the block cipher, encrypting 0, so the counter. So the counter gives you what you need to encrypt. So 0 and then 1 and 2 and so on and so forth. So each of these blocks that essentially are encryptions of a counter, they go through the block cipher, which is encrypts with a key and gives you key stream, just like acting as a pseudo-random generator, and then that key stream gets XORed by the plaintext, giving you the ciphertext. Okay, so basically you create the key stream by encrypting blocks that essentially count, okay, from 0 to how many blocks you need. And then to decrypt, you recreate the stream you recreate the key stream and you XOR it to the ciphertext, just like we said for stream ciphers. Interestingly, this means that you never use the block cipher in decryption mode, because you have to, even for the decryption in the counter mode, you need to use it in encryption mode, okay? Which means that you have to recreate the key stream just the same way you created it for the encryption purpose, okay? Again, and you can see in more details that this was exactly what we dealt with in the stream cipher chapter. And that's all for this time. Thank you.